Hello everyone, so my name is Apostolopoulou from City University of London, and today I'm going to talk about distributed optimal power flow for unbalanced radial systems with time-varying communication. So this is a joint work with Ramat and Upama from Oxford Institute for Energy Studies. Okay, so let's start with some motivation behind this work. We know that power systems in the past decades have been changing radically with the deployment of distributed generation resources and flexible demand. So what do we mean with flexible demand? We could mean, for instance, deployment of electric vehicles or EVs, as we're going to be referring to them from now on. So these changes are leading towards what we call a fractal grid. Fractal grid are what the future power systems are going to be looking like. They're going to consist of recursive assemblage, as you can see in the figure here, of many smart buildings, microgrids, smart cities, distribution grids, national and international networks. So this will lead to flexible, controllable, and interoperable systems that may be operated in an efficient and safe manner. However, as you can see, these fractal grids are more complex compared to the traditional power system architecture because they have a lot of small devices connected to the system. Okay, so the next question is, can centralized power system operation approaches that are now dominant in power system operations handle this sort of structure? We have some computational complexity and privacy concerns that are important and that cannot be dealt with centralized approaches. So in this regard, it's important to propose appropriate methods for fractal grids that leverage the distributed generations and ensure a reliable, sustainable, and secure power system operations. Such approaches need to be decentralized so they can deal with the computational privacy challenges associated with the operation of these type of grids. Okay, so in this regard, in this work, we propose a distributed multi-period optimal power flow, or OPF, for distribution systems. So the entities that participate in this OPF are the distribution system operator, DSO, distributed generators, and electric vehicle owners. So how do we model the OPF? We have an optimization problem that has an objective function. Usually it's minimize the cost and subject constraints such as variable limits and network constraints. So the way we have specifically formulated this is that the DSO has an objective to minimize the cost, so the cost that you procured at the substation from the transmission system, and it has to meet the network physical limits, such as power balance and the voltage magnet constraints. It also cares about the deviation of the voltage from some reference value, which we call the voltage regulation cost. And distributed generation owners wish to minimize their cost of operation, so we minimize the distributed generation cost here, such that the injections of real and reactive power are within their limits. Last, electric vehicle owners wish to charge their vehicle at minimum cost without degrading their battery and operating at the charge-related constraints. Okay? So this is what we might call a centralized formulation of the OPF, but we propose a distributed solution to it. We're going to see it in the next slide. Some important points in this formulation that are different from others found in literature is that we model the inter-temporal constraints, for instance, the electric vehicle charging needs. So we render this OPF into a multi-period optimal power flow. We use a linear model that represents the three-phase unbalanced network, which is based on a fixed point interpretation of the AC power flow. The distributed solution of this OPF is guaranteed to converge to the optimal solution under a time-varying communication network topology, and only local information is exchanged between neighbors and is used by the algorithm, thus maintaining and meeting privacy concerns. Okay, so we solved the centralized formulation of the OPF, and now we're going to see how we're going to solve it in a distributed way. So we're going to see a high-level description of the algorithm used. Let's assume we have n agents that are communicating with some time-varying network topology. More details about the properties that the communication network needs to meet may be found in the paper. An example may be seen in the figure here. So here at one time instant, the red links, so between agent 11 and agent 1, agent 2 and agent 3, and so on, are active, and in the next time instant, the dashed blue ones are active. So between agent 1 and 2, 3 and 4, and so on. And this continues periodically. So that's an assumption of a time-varying communication network. So the overall OPF problem, as we saw it before, is a decision-coupled problem between the agents, where agents have a common decision, which is modeled by the coupling constraints, or the network constraints in this case. Agents have also separate constraints. For instance, the electric vehicles have their charging constraints, and agents have separate objectives, as we saw before and we discussed briefly. So in step 1, each agent solves its own local problem. For instance, an electric vehicle aggregator minimizes the cost of, if it says that they have their local objective, which is the cost of charging, and they have the local constraint set. They have to keep the variables within limits. In this local problem, we add this proxy term here, as you can see, that penalizes disagreement in the coupling constraints with the other agents and is a function of the neighboring agent's information. In step 2 next, each agent broadcasts a solution to the neighbors of this local problem and receives solutions from the neighbors. And in step 3, we update this proxy term in the local problem, and based on the information we have received in step 2, and then we go again to step 1 and solve again the local problem, and so on, until we achieve convergence. So when do we achieve convergence? An example of achieving convergence is when the infinity norm of the consecutive difference of the local decision variables is smaller than some tolerance for a number of iterations. Okay? So this was the high-level description of the proposed distributed optimal power flow that can converge under a time-varying network topology. And it has 3 basic steps. More details of the algorithm may be found in the paper too. So let's see now an example of implementing this framework. So we choose a 141 distribution feeder. We run a 24-hour OPF with hourly intervals. The time-varying network topology may be found here. So as you can see, we have 11 agents. And these 11 agents are the 10 electric vehicle aggregators plus the DSO, or distribution system operator. The coupling constraints are around 3000, and they refer to the 3-phase power nodal balance. So in the figure below, we can see the evolution here of the Lagrange multipliers of the coupling constraints, and here of the objective function value with respect to the number of iterations, which is up from 0 to 1500. So in the first figure here, we can see that around 600, the Lagrange multipliers converge. Okay? Here we can see that the objective function needs up to 1500 iterations to converge. However, we see this jump here at 600. Why does this jump occur? This is due to the fact that we know that the Lagrange multipliers have converged in this time instance. So from here on, we only use the local, we only use estimates for the decision variables after this iteration. That's why we see this jump. And you can find further results and more detailed explanations in our paper. Okay, so let's sum up and make some concluding remarks. So in this paper, we developed a distributed multi-period optimal power flow for radial distribution systems. In the numerical results section, we demonstrate that it's scalable and it performs well in a variety of circumstances. It's useful for practical implementations since we used the realistic time-varying communication infrastructure assumption, And for future work, we plan on incorporating uncertainty sources, as well as modeling flexible demand as price responsive. Many thanks for your attention and for attending this presentation.